Brandon. Welcome back to Geometry. And today I'm going to be introducing something very exciting. Um, proofs. Proofs. Yes, proofs. If you haven't heard that before, that's probably a good thing. If you have heard it before in association with geometry, you've probably heard something like it makes me want to puke or I hate proofs, that kind of thing. Let me tell just a quick story before we jump into this because it is a really challenging part. It is not easy. It is at least probably so far in your education, the epitome of thinking logically, clear, rational, deductive thought. And that's not easy, but it's a good thing. Anyway, so when I was teaching geometry at a school, I had been through geometry a number of times. I always noticed that students kind of get hung up on this word proofs. So what I did was this. One year I didn't say the word proofs, or I told myself I wasn't going to. And I did. I just avoided saying the word. And I said, okay, well, look at what we did here. We went through the process. And I said, it's kind of like a brain teaser, but realize that if you start with these ideas, then this final thing that we get, it has to be true. It cannot be doubted. Like we figured out this eternal truth has to be true. The students were like, whoa, this is cool. And so then we were going through proofs, we were practicing, and I wasn't saying the word proof, but then one day I accidentally said the word proof. Oh, said it. And one of the students was like, "Oh, that's what a proof is. Oh, I hate proofs." So keep that in perspective. What we're doing here is actually something really beautiful and is part of the shows the simplicity and the order of geometry. And really, this is how mathematics is done in general. Not always in this format, but this kind of idea of developing a proof. So hang on, pay attention because it's like this really difficult, challenging, open-ended type question thing that we're approaching. Now, because we're in geometry and we're introducing proofs for the first time, we only have a few limited tools in geometry. So the book, the Saxon text at least introduces proofs using algebraic proofs first, right? And I've seen other textbooks that do this as well, the programs. So we're going to do this with algebra, and then we'll progress to using this proof idea with geometry. We're going to be using algebra stuff anyway in geometry, so may as well start here. First of all, what is a proof? Very simple. It's a deductive argument. Okay, there are proofs in geometry. That's a mathematical proof, and it's kind of regarded as like the paradigm of what a proof can be. People say like, "Oh, well, can you prove it? Can you prove it?" And well, it's like, well, it depends. What are we talking about? Are we talking about mathematics? Are we talking about philosophy? We're talking about history. We're talking about physics, right? There are different ways of proving things depending on the type of subject that you're discussing. Basically, it's just a deductive argument. Just some review of properties of equality, things you already know. We're going to go through. So the addition property of equality. Notice I'm like abbreviating here, right? Because I'm lazy, so we do this. It's okay, but you do have to write the stuff out. But you can abbreviate. That's okay. So the addition. So that just means that if you have an equal sign, you can add the same thing to both sides. So for example, if we were to solve like x minus 5 equals y, if I add 5 to both sides, I get this. What did I do? I added to both sides. So the addition property of equality. Subtraction property of equality works the same way. If I have x plus 5 equals y, if I subtract 5 from both sides, then I end up with this. So going from here to here, I'm applying the subtraction property of equality. The multiplication property of equality. If I have x over 5 equals y, I can turn that into x equals y times 5. What am I doing? I'm multiplying both sides by 5, right? Like 5 times x over 5 is x. That's that. And then 5 times y is y times 5. You get that division property of equality. If I have 5x equals y, I'm trying to get x by itself. How would I get x by itself? Well, I'd have to divide by 5. And as long as I do that to both sides, then I'm okay. So x equals y over 5. That's the division property of equality. The symmetric property just says that you can flip back and forth over the equal sign. 8 equals z is the same thing as saying z equals 8. The reflexive property. Think reflexive is like reflection. You're looking in the mirror. It's the same thing looking at itself. So x equals x. In philosophy, we call that the principle of identity, that a thing is what it is. A is A, you could say. The transitive property of equality, if x equals y and y equals z, that means that x equals z. Right? If two things are equal to the same thing, then they're equal to each other. It's very simple. Right? Again, notice this is equality. We're going to have something different later on, congruence, but for now we have these properties of equality. And then the substitution property. Notice we can't just write sub because we'd have subtraction and substitution. So we have to include more than just the SUB. So substitution property of equality, if x equals y and x equals and x plus 5 equals 6, then we can substitute x and y. If we have two things that are equal to each other, they can be substituted in for each other in equations and expressions. Okay, so now let's apply this stuff. If we're given this statement, so what an equation is, it's just a statement that this is this, and I want to prove that x equals 5. In other words, I'm kind of solving, but I'm giving it to you this way for a reason. Okay, so I start with this, and what I'm going to try to do is I'm trying to isolate x. It's going to follow my algebraic steps. What's the first step I'm going to do? I'm going to distribute the 3, so I get 3x plus 6. That's what I get here. That's the distributive property, right? It wasn't one of the properties we had over here of equality, because it's not a property of equality. It's just the distributive property. But that's what I'm doing. So in other words, think of it this way. In order to go from here to here, well, starting with this, how do I get this? Well, that's the given. That's the thing you're given. Okay, fine. And then how do I get from here to here? Like imagine if you did this step and then someone said, whoa, 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 what'd you do? Why'd you do that? You say, oh, I'm just distributing. That's what you put here. That's it. You're justifying every step. And then going from here to here, notice what I'm doing. I'm subtracting 6 from both sides, right? I'm adding into both sides this minus 6. So like, how do I get from here to here? Well, I'm subtracting. I'm subtracting 6 from both sides. So that's the subtraction property of equality. Going from here to here, what did I do? Well, 11 minus 6 is 5. 6 minus 6 is 0. So that disappears from this side. What did I do? I simplified. That's it. Right? Just imagine somebody asking you every step. Well, how do you know that? How do you know that? How did you get that? So going from here to here now, I'm subtracting 2x from both sides. So getting from here to here, that's a subtraction property of equality. And then getting from here to here, I just simplify, right? So 3x minus 2x, and then 2x minus 2x, that disappears over here. So I end up with x equals 5. I got that because I just simplified the expression above. Okay, now this is the thing I was trying to prove. And so when we get to the end here, if we're given something we're trying to prove, and we get to it, then we can say QED, kind of like an old-fashioned traditional way of saying we're done with the proof. QED is Latin for quod erat demonstrandum. So it means quod is what, erat means was, and demonstrandum is a gerundive. It's has the idea of what was having to be proved. It's like the future passive participle of the thing. It's but it has the sense of ought, right? So what we're saying is that was the thing that we were trying to prove in the first place. So quod erat demonstrandum. We did it. We found it. That was the thing. Uh, and so that's why I put it this way, given and prove, because now we got the thing we were trying to prove. And so we can say QED. It's kind of like dropping the mic at the end of the proof. Here's another example. Instead of saying prove, I'm just saying solve for. So we go through step by step. We start with the expression 3 times x minus 2 equals 5 times x minus 1. So I have that here. That's just the given information. So like, where'd you get that from? That's what's given. Going from here to here, I distribute the 5, distribute the 3. So I get this expression. Again, someone says, well, how'd you get that? So, well, it's the distributive property. Right, I distributed. I'm trying to get x by itself. So I'm going to get rid of the 6. How do I get rid of 6? I add 6 to both sides. Okay. So where did these 6's come from? That's the addition property of equality. Simplify. So where did this expression come from? I simplified it. Simplified the previous step. Now I'm trying to get x all to one side. That's important. So I'm going to subtract 5x in order to get rid of this. So that's the subtraction property of equality. Remember SUBT. You can just write SUB because that could be subtraction or substitution. Simplify again. All right, well, now I've got this -2 here with the x. How do I get rid of -2? I divide. So I'm going to divide both sides by -2. And I get, so -2 divided by -2. So -2 divided by -2, that makes that disappear, and I end up with just x there. 1 over -2. What am I doing? I'm dividing, so that's the division property of equality. I just simplify, and I get x equals -1/2. That's it. That's the value of x. I wasn't setting out something to prove, so I'm not going to say QED at the end of it, but that is the solution. That is the whole proof. So what does it mean? That given this expression we just proved, you cannot doubt, it has to be true, that if this is true, then this thing at the end has to be true. X has to equal -1/2. So proofs are really powerful. They're the foundation of mathematics, and really logic is the foundation of all rational thought. We're just trying to teach it explicitly here in mathematics. Geometry is a great place to do that, right? So try to see the beauty in it if you can. Don't just write it off like, oh, people say they don't like proofs, so I'm gonna go with the crowd and be a rebel, and go with the crowd at the same time and be a rebel and not like proofs. Right? Just try to see it, and see it as like a brain teaser or something like that, and appreciate the beauty, the order of the whole thing. So, thanks for watching. Don't forget to like and subscribe.